Hello world, I'm Benjamin and this is Source Decoded, and it's a little bit early in the morning, so if I mumble, I'm sorry. So in the last video we talked about simple logical machines with logic gates, and I talked about how you can combine a bunch of these simple machines to make a calculator, and that's actually how calculators and computers work on a fundamental level. And the reason we talked about that is because I wanted to actually make a calculator out of JavaScript on my computer, which of course is just a purely academic exercise. This isn't really useful at all for doing actual calculations, and as you'll see, it's actually pretty quite tedious to use. But I think it is interesting to understand a little bit about how this works on the metal, so to speak. So let's go ahead and build us a JavaScript calculator that can't actually calculate very much. Now, the smallest pieces of machines that we talked about were the logic gates, the AND, OR, NOT, and XOR. So the first thing we need to start with is making those very small machines. We'll start with AND. Takes two inputs. And you can think of these small machines as functions because they take inputs, they do work, and they produce outputs. So we'll implement them all as functions. These more fundamental functions are going to look really silly because I'm just going to return A and B, because these fundamental operations, Boolean operations, are useful not just for the tiniest building blocks inside of a computer or a calculator. We also tend to use a few of them quite a bit on higher levels as well. So there's AND, let's do OR. It's going to look pretty similar, A or B. If you don't know JavaScript at all, this double ampersand is just how you say and this double pipe is how you say or. Now finally we've got not, and it only takes one input and returns one output, which is the opposite of what came in. Remember, we're dealing with binary or Boolean values, which are only allowed one or two possible states. We call it true or false, or 1 or 0, but you could just as easily call it peaches and pears, or applesauce and rhinoceros. It doesn't really matter. The point is it can be one of two things. Okay, so now we've got our simplest machines. Let's start assembling them together to make more useful ones. Okay, our first composite machine is going to be the XOR, or exclusive OR. It takes two inputs. Now, you remember this one is true if either is true, but not both is true. So if we were to write that out, we'd say true if A or B, but not A and B. So we can pretty much just assemble it kind of like we wrote it there. Return, I'm going to start with an and an or, A, B, and not and A, B. So this will be true if A or B and not A and B. If we were to write this just in vanilla JavaScript, for you that might be more familiar with that, it would look like A or B and not A and B. That's what an exclusive OR looks like. To be useful, of course, we need to assemble these into slightly larger machines. We'll start with the half adder, which, as you remember, takes two inputs. This one actually returns two outputs, and most programming languages prefer if you only return one output. JavaScript only lets you return one output, so we're going to output a JavaScript object. This is kind of a higher order feature that you would certainly not see inside of a primitive calculator, but it's what we got. It's either this or an array, and this will be more descriptive for you to understand. So let's make a JavaScript object, and it returns two outputs. Remember, we called them sum and carry. The sum was the result of an XOR between the two inputs, and the carry was the result of an AND between the two inputs. And now we have a machine called a half adder. Now, to be really useful, we're going to take those medium-sized pieces and turn them into slightly larger pieces for our full adder. It takes three inputs, an A, a B, and a carry in, and it will return two outputs. Again, a sum and a carry. Now, if you go back to the last video and look at how the full adder was implemented, you remember that we did three operations inside of the half adder. The first one was to add A and B together with the half adder. Oh, we gotta hang on to that value. The second thing we did was add the sum of our first add operation with the carry of the input. So the sum of the first with the carry. And then our carry output was the result of an OR between both carries. Now we can output the sum of the full adder is the result of the second sum, the sum of the second add, and our carry out. So there we've got a full adder. These machines are starting to get a little more useful. And if we wanted to test this out real quick, let's just see what we get if we output a full adder with true and true as the inputs without a carry. All right, now let's see what happens. Now for this, I'm not in a browser. I'm just using Node on the command line. If you don't have Node, it's pretty easy to install. Go to nodejs.org and download an installer for your operating system. That gives you a command line program named Node. And then just go into the folder where you've got this file saved, and then I'll just say node index.js, and it'll run that and give me some output on the command line. So I got false for my sum and true for the carry, and that's what I expect. So that means that not only is this full adder working, but the half adder, the XOR, the OR, and the AND, and the NOT are all seem to be working. So that's pretty cool. Now the last thing we did in the last video was chain a bunch of these full adders together to make something that could add two 4-bit binary numbers. So let's go ahead and do that now. Let's make a new function. We'll call it a 4-bit adder, and it is going to take 8 inputs, 4 for the first bit and 4 for the last. You might ask, why don't we just make it take 2 inputs, a number for the first and a number for the last? Well, computers are really primitive, and on this level they don't even know what a number is. So when you add binary numbers, the computer is operating on them as bits, just individual little bits. So if we want our calculator to understand what a number is, then we're going to have to teach it how to do that, and we're not going to do that today. So we take 4 inputs: A4, A3, A2, A1, B4, B3, B2, B1. So why am I putting them in reverse order like that? Why don't I do A1, A2, A3, A4? Because when we write numbers, like on a piece of paper, we write it so that the least significant digit is on the right and the most significant digit is on the left. So in 123, the 1 is worth 100, the 2 is only worth 20, and the 3 is only worth 3. So to make it a little more familiar to read out these numbers, I'm putting the inputs in what looks like reverse order, but it's actually more natural how you're used to doing it. Now, let's chain these full adders together. First, we'll start with the ones place. And that's going to be a full adder with A1 plus B1, and we need to give it a carry value, which in the first position will always be false. And that's add 2. And the carry in for this will be the result of the add 1 sum, or the add 1 carry, sorry. This little 4-bit adder machine is going to return 5 values. There'll be the 4 sums of each of the full adders inside, plus the carry. I'm going to call the outputs of these place 1 is add 1 dot sum. Place 2 is add 2 dot sum. And that is our 4-bit adder. Now let's see if it works. We need to add 2 4-bit numbers together. So, oops. 4-bit adder. Let's add 1 and 1. So there's our first number, binary 1, and then the second number is a binary 1, and we would expect to get a binary 2 back. Now, console logging this is a little bit ugly because of how primitive our return data structure is. Okay, so here's what we're going to output. I'll put the carry bit on the very leftmost because it is the most significant output bit, and then we'll just output 4, 3, 2, 1 in order. So let's see how that works. And I get an error. Okay. So what do we get? No carry, false, false, true, false. So that is, if we think of these as zeros and ones, 0, 0, 0, 1, 0, that is a binary 10. So our 4-bit adder worked. Now, one of the cool things about computers and software engineering is the fact that we get to take small things and make big things out of them. And that really helps us, that really saves us from having to think about big things in terms of all of the individual small pieces that goes into them. So if we look at our full bit adder here, we've got 4 full adders. A full adder is a couple of half adders and another OR. A half adder is an XOR and an AND. An XOR is a bunch of ANDs and an OR and a NOT. So what would happen, what would this 4-bit adder look like exploded into all of its little pieces just in one little place? Let's go ahead and write that. 4-bit adder expanded. It's going to take the same 4 inputs, and the output is going to be the same, but the body of the function is going to be completely different. Okay, so here it is, and it is much larger. but we haven't used any composite machines in here. First, we have to do the half add in the full add, and that half add, you'll recognize this as the XOR and an and then we have to do the second half add, and that's another XOR and another sum based on the inputs of the last one. So this was really hard to write. It took me some time to get it right. You can see there's some repeating patterns in here, but looking at this, it's really hard to understand. That's the great thing about programming, and really this is a big part of what programming is to be able to take a large problem and turn it into a bunch of small ones. And I think it's really fun to do that, and it's fun to think about that when we write software, all we're doing is essentially organizing these little networks of discrete logic gates that live somewhere on the metal deep inside our machine. So let's go ahead and test that to make sure it works. So this is going to be the result of 4-bit adder expanded. I'm going to copy the input from the last one because all of that was a lot of typing that I don't want to do again. Let's go ahead and take this 2. Insert 2. And let's see what that gives us. Ah, we got the same answer. So that seems like a lot of work to do a primitive thing, and you're right, it is a lot of work to do a primitive thing. Hopefully, if nothing else, you've got some appreciation for the complexity that lives deep, deep inside your computer, and this is really only just scratching the surface. There's a lot more we could do to expand the capabilities of this little calculator, but what you see here is pretty much the fundamentals. This is how you add with just binary. I also wanted to make my calculator able to subtract, so I went and learned how computers do that, and it's actually really clever. They figured out how to subtract by adding, so we don't actually have to write any more arithmetic logic to be able to do subtraction. And once you can do addition and subtraction, then you can do multiplication and division. And once you can do multiplication, then you can do exponents. In the next video, I'll show you how to subtract by adding, and we'll implement it in the calculator. And this trick works for binary as well as base 10 decimal. I think it's kind of cool. In the meantime, share this video and the one that came before it with somebody else you think might be interested in how a computer works on a fundamental level, and you'll see me in the next one. Bye.